Hi guys, Dr. Colbreth here with an introduction to exponential decay, specifically exponential decay in the context of damped oscillations. I want to start off looking at an ideal oscillator, and what do we mean for an oscillator to be ideal? Well, the main approximation that we make here is that the amplitude of this oscillator is constant, and it oscillates from minus A to plus A forever. But a more realistic model is that of a damped oscillator, which starts off at some maximum amplitude, and then the extent of the oscillation dies out over time. Now I want to compare both the ideal oscillator shown at the top with the damped oscillator and take a look at their displacement as a function of time. And for the ideal oscillator, we see that the amplitude doesn't change. The maximum displacement of the oscillator is constant in time, represented by this horizontal dotted line, and the amplitude is constant as the oscillation continues on forever. But here for the damped oscillator, we start off at some maximum value A, and our oscillation is contained within this decaying envelope here. And over time, in an infinitely long time, the oscillation amplitude goes to 0. Mathematically, we can look at the simple oscillator and see that its position as a function of time is given by, and I want to make a quick note here, although I'm showing a simple pendulum here in my animation, this applies to any simple harmonic oscillator, so we're going to use the general position coordinate x. So the position as a function of time is equal to a constant amplitude a times the oscillating piece, the cosine of omega t plus phi 0. Now for the damped oscillator, our amplitude is not constant, so when you replace this constant amplitude a with a function that varies in time, and it's the maximum displacement of our position that decreases in time, so we're going to replace this with a function x max of t, which describes the extent of the maximum displacement in time. And as I show in another video, the solution to the differential equation for a damped oscillator requires that this x max of t function be an exponential decay function. So here we have x max of t is equal to a, which is our initial amplitude, times the natural number e to the power of minus bt divided by 2m. And this describes this envelope here that the oscillator moves within. When t is equal to 0, we have e to the 0, which is 1. So we have that the maximum displacement at time equals 0 is just equal to a, which is what we see here on our plot. And as t goes to infinity, we have e to the power of minus infinity, which is 0. So as time stretches out to infinity, our maximum displacement goes to 0. So we want to take this envelope, which describes the maximum displacement, and we want to combine it with our oscillating piece, which is still just the cosine of omega t plus phi 0. So instead of having a constant amplitude, we're going to have this decaying amplitude. So if we multiply these two pieces together, we get the kinematic equation for a damped oscillator. X of t is equal to our exponential decay piece, a times e to the minus bt over 2m, times the oscillating piece, which is the cosine of omega t plus phi 0. So we have a new parameter here in our exponential decay, b, which is called the damping constant. And on the left here, I have animations which show different values of the damping constant. At the top here, we have b equals 0. So if we take b equals 0 in our kinematic equation, we always have e to the 0 here for this first term, which is e to the 0 is 1. So if this exponential term is 1, we recover a times the cosine of omega t plus phi 0, which is just our ideal oscillator, our undamped oscillator kinematic equation. Now, the second animation and the third animation show increased values of the damping constant. Here we have a modest value of the damping constant. Here we have a more extreme value of the damping constant. And we can see that the value of b determines how quickly the oscillation dies out. A couple more notes on the damping constant. First of all, it has kind of unusual units, kilograms per second. And the value of b depends both on the shape of the oscillator and the medium that the oscillator is within. So this is like an engineering parameter that can be measured or in some cases calculated. And it depends on both the oscillator and the medium that it's within. So the shape of the oscillator, for example, we could say that if a damping constant for a parachute is going to be much bigger than the damping constant for a bullet. Right? A bullet moves through the air quickly and is not as damped as a parachute, which has a lot of damping. So the shape of the object certainly affects the damping constant, and also the medium that it's in. So if we were to take these pendula here and we were to have them oscillate in water, they're going to be damped more quickly than the same pendulum damped in air. So we have that b for an object in water is bigger than b for an object in air. In other words, the medium matters. Now these are just kind of extreme examples, and b for one particular oscillator and its medium can be measured specifically for the system at hand. So I have a question here then. We know that the damping constant affects how rapidly the oscillation dies out, but how long does it take for the velocity of the pendulum bob to reach zero? And of course, according to our model, the bob takes an infinitely long time to come to a stop. So if we want to describe how quickly the oscillation dies out or how quickly the oscillator loses energy, we can't talk about how long it takes to come to a stop because that's an infinitely long time. So we need to build up another way of talking about how damp something is or how quickly the oscillator loses energy. And to do that, I want to look specifically at the energy of an oscillator. So we're going to move away from pendulum for a moment, and we're going to look at the energy of a mass on a spring. And the main reason for this is we just don't have to worry about gravitational energy, and it just simplifies the analysis here. So in the case of an undamped spring where we have constant amplitude, if we evaluate the energy at the turning point or at the amplitude, at the endpoints where the velocity is zero, first of all, the energy or the position of an undamped spring has a constant amplitude A, as we've discussed already. And given that, the total energy is just equal to 1/2 k times the amplitude square. So we evaluated the turning point. The turning point is in the same place every time, right? The turning point is at the amplitude A. And so the total energy of an undamped oscillator is equal to 1/2 k A squared. Now, if we compare that to the damped situation where we start off with a maximum amplitude A, but the extent of the oscillation dies out over time, if we want to calculate the damped oscillator, first of all, we'll refer to its kinematic equation for the position here, and we'll see instead of having a constant amplitude, we have this amplitude which decays over time. And so in other words, the maximum displacement of the amplitude reduces over time. And our x max of t is given by this exponential piece. And if we want to calculate the total energy of this oscillator, well, the total energy is not constant, right? The damped spring is losing energy to its environment because of the damping, because of the friction, because of the air resistance, whatever is causing this oscillation to decay, energy is leaving the oscillator and moving into the environment. So the energy is not going to be a constant. Instead, our total energy is going to be a function of time. And so here we have our total energy as a function of time is equal to 1/2 k, and instead of using the amplitude A, we're going to use x max of t in here because it starts off with the total energy being equal to 1/2 k A squared, but as the maximum displacement decreases, the total energy of the system decreases as well. So substituting in x max of t for A, we get that the total energy is equal to 1/2 k times our exponential decay piece squared. And we're going to do a little more analysis on this equation. The first thing we want to do is distribute this squared in here. So we're going to get 1/2 k A squared times e to the minus 2b t over 2m. And we'll note that the 2's cancel here in this case. And now we can rearrange our terms a little bit. And we want to analyze this a little bit more. So out in front, we have 1/2 k A squared. These are all constants. And this is the piece that changes in time and causes our energy to decrease in time. So I want to evaluate that a little bit more. And this is really where we get into some of the details about exponential functions. So the first thing is if we have an exponential function here, like e to the minus bm over t, b divided by m times t, anytime we have an exponential, the argument of the exponential or the exponent of this exponential can't have units. It doesn't make any sense to talk about e to the power of minus 2 kilograms. That just doesn't even make sense. We don't know how to raise something to the power of a kilogram. So what that means is that the argument of the exponential function must be a dimensionless number with no units. Okay? So in this case, that means that m divided by b must have units of time because t divided by this quantity must be dimensionless. We know that t has units of seconds, so t divided by this quantity here must be dimensionless. So if t is multiplied by b over m, then m over b must have units of seconds in order for this argument to be dimensionless. And so we're going to make a definition now. We're going to define tau as being equal to m over b, and tau is measured in seconds. It's a length of time, and we're defining tau in this way. So now we can rewrite our exponential function using tau, which is called the time constant. We can rewrite our exponential function as e to the minus t divided by tau. So now our energy function becomes even more simplified. We have our energy, or total energy of our oscillator as a function of time is these constants out in front times e to the minus t over tau. And we can rewrite these constants as just the initial energy of the oscillator, and this brings us to our totally simplified form that the total energy of the oscillator is the initial energy times the exponential e to the minus t divided by the time constant tau. So why do we do this? What does this all mean? Well, this is how we're going to talk about how quickly something decays is based on this value of tau. So tau combines the damping constant. We've already seen how the damping constant affects how quickly the oscillation dies out, and it depends on the mass. So the larger the mass, the longer it takes for the oscillation to die out, and the larger the damping constant, the more quickly the oscillation dies out. So for our example that we've shown here, I want to highlight a special point, and the special point here is shown on the plot. And the special point is where t is equal to tau. So after one time constant of time has elapsed, and a time constant is equal to m over b, and this is evaluatable as a certain number of seconds, right? And so when that certain number of seconds has elapsed, we can evaluate our total energy. And we get our total energy is equal to our initial energy times e to the minus t over tau, but here we're taking t is equal to tau seconds. So after tau seconds have elapsed, our total energy is equal to E0 times e to the minus 1. E to the minus 1 is equal to 0.37. And so what we can say is that after one time constant, which is tau seconds, has elapsed, the oscillator's energy is reduced to 37% of its original value. And we can follow this sort of procedure again, and we can consider what happens when the time is equal to two time constants. So here, more time has elapsed, not just tau seconds, but now we've gone by 2 tau seconds, and our energy is significantly decreased from its initial value of E0. And if we evaluate this expression when t is equal to 2 tau, we get that the total energy is equal to our initial energy times e to the minus 2 tau over tau, which is equal to e to the minus 2. Which is equal to E times our initial energy times 0.135. So in other words, after two time constants, which is 2 tau seconds, have elapsed, the oscillator's energy is reduced to 13.5% of its original value. So returning back to our expression here for the energy, we note that it takes one time constant to reduce an oscillator's energy to 37% of its original value. But we did some manipulation to get to the energy expression, and I want to look back at our original kinematic expression for the displacement, or the amplitude. And the displacement, or the amplitude, was equal to AE to the minus BT over 2M. And here we have M over B is our time constant here. So this simplifies to A times E to the minus T divided by 2 tau. And so we can summarize this by saying that it takes two time constants to reduce an oscillator's amplitude to 37% of its original value. So tau is the amount of time it takes to reduce the oscillator's energy to 37% of its original value. But tau can also show up in our kinematic equation for the position. In other words, the amplitude also can be written in terms of this time constant tau. But in the case of the amplitude, it takes two time constants to reduce the oscillator's value to 37% of its original value for the amplitude, and it takes one time constant to reduce the oscillator's energy to 37% of its original value. So I just highlight this because this is a confusing distinction. We went through this work to define tau, then why on earth does this guy depend on 2 tau? Well, we often deal with the amplitude when working problems, but the reason that tau is defined the way it is because of its relationship to the energy of the oscillator. So in summary, we have that tau, which is called the time constant, is equal to m divided by b, and the time constant tau is a convenient way to characterize how fast an oscillation decays in seconds. So if we just want to know how damped the system is, we can compare the time constants from one system to another, and it will tell us how quickly the system decays, because we know it takes an infinitely long time for the system to completely stop. But we can consider the system completely stopped, at least approximately, after many time constants that have elapsed. For example, after 10 time constants, the amplitude of an oscillator is at 0.6% of its original value. So the time constant just gives us a sense of how fast the oscillator decays. So I just wanted to provide an introduction to exponential decay and this notion of the time constant and how it fits in with the energy, and also how exponential decaying oscillators or damped oscillators compare to their ideal counterparts. I hope you enjoyed this presentation, and I'll see you in the next one.